Hi, myself Dr. J. Glory, Associate Professor of Physics, Institute of Aeronautical Engineering. Today I wish to tell about the properties of nanomaterials. When the bulk particle is reduced to nanoscale, there are so many properties can be affected. So when the bulk material is reduced to nanoscale, so mechanical properties will be changed, optical properties will be changed. So, what are the properties, how they are changed here, we are going to see in this session. So, the topics which we are going to cover in the session is physical properties, how the physical properties can be changed, and then chemical properties, optical properties, electrical properties, magnetic properties, and then mechanical properties. Then we shall see the references related to this topic. So, properties of nanomaterials. In these properties of nanomaterials, the physical, electronic, magnetic, optical, mechanical, thermal, and chemical properties of nanomaterials are size dependent. So, here the properties of the materials are size dependent. When compared to the bulk size to the nano size, because of the size has been affected and gives variation in different areas, that is physically, electronically, and then magnetic, in optical in the sense colors, so like that. So it is size dependent. So these properties of materials are size dependent. Small particles display behaviors that are different from those of the individual atom or bulk. So small particles behaves differently. So when compared to the bulk, when compared to the bulk. So nanomaterials, that is we have nanomaterials, we can fabricate nanomaterials from bulk to nano, or else it is from the bottom up. We can fabricate the nanomaterials from atom by atom to the nano scale range of materials. So bulk to nano size, bulk to nano size, and individual atoms can be built it up, and we can make nano sized particles. So here items. So atoms, adding atom by atom, we can get the clusters. Then we can go for nano-sized particles. This is in the process of bottom up. So already we have seen what is bottom up, and then what will becomes under the bottom up process. That is a methods in the bottom up process. So in that bottom up process, we have seen sol gel, technique, and then we have seen some vapor deposition techniques. So here this one is bulk to nano size. So this is top down process, that is bulk material is reduced to the nano size. So by physically we can do we can use ball milling method and combustion method, and also we have seen that another technique which is that precipitation precipitation method. So here top down, ball milling method, combustion method, and then we have precipitation method. So in these three process, we can mm, fabricate the nano sized particles from the bulk material. So here when coming to the bottom up, so we can fabricate by using the method, a sol gel method, vapor deposition method. So in this vapor deposition method also we have two types, that is physical vapor deposition method. Physical vapor deposition technique, and then chemical vapor deposition technique. So these are the methods we have in the different fabrication of nanomaterials, that is in top down process and then bottom up process in both the cases. So the main thing is when bulk material is reduced to nanoscale, it displays different behavior. It displays different behaviors from those of individual atoms or bulk. So first we shall see physical properties. Physical properties. In this physical properties, the first effect of reducing the particle size is to increase the surface area to volume ratio. So the first effect of reducing the particle size is to increase the surface area to volume ratio. So surface area to volume ratio, if we take bulk material, so this one is a single solid material. So single solid material, that is in solid material in the sense closely packed atoms. So solid is a closely packed atoms. So made a solid. So atoms are very close to each other, so that they tightly bound in the bulk material. So that when it is reduced, when the size of this bulk material is reduced in the sense of we may crush this bulk material in different ways. So if we crush this bulk material, what happens, each part will, the volume will be the same, but we are making small particles. We are making small particles, so that we'll get a small particles. So this one of the solid, that is one of the small particle may take. So we have, so like this. So the volume will be the same, but the surface area. So the surface area will be increased. The surface area will be increased. So uh, the first effect of reducing the particle size is to increase the surface area to volume ratio. So this changes the surface pressure. So because of increase the surface area to volume ratio, change the surface pressure, so that it results in a change in the internal interparticle spacing. So when the surface area is increased, it results the surface pressures change. So because of the surface pressure change, there will be change in the interparticle spacing. So the change in interparticle spacing and The large surface to volume ratio in particle have a combined effect on material properties. So the change in the interparticle spacing, because before that in bulk size the interparticle spacing is very less, because the atoms are very closely packed, so that the energy band, there will be energy band, that is the energy levels are overlapped, so that the interparticle spacing is very less. So here when we increase the surface area to volume ratio. So what happens? The surface pressure will be changed, so that there will be change in the interparticle spacing. Okay, so that the change in interparticle spacing and then large surface area to volume ratio have a combined effect. So both are combinedly will get a effect on the material properties. Material properties. So variations in the surface free energy changes the chemical potential. So variations in the surface free energy changes the chemical potential. So this affects the thermodynamic properties like melting point. So it affects the thermodynamic properties. In which way it is affecting means that, so we can see the melting point change in the melting point. So variation in the surface free energy, it changes the chemical potential. So the effect, so this effect the thermodynamic properties like a melting point. So the melting point decreases with the size, and at a very small size the decrease is faster. So the melting point decreases with size. So melting point decreases with size, and at a very small size, what happens? The decrease is very faster compared to the bulk size. So that's why here in chemical properties, the largest surface to volume ratio, the variations in the geometry and the electronic structure have a strong effect on catalytic properties. So, the largest surface to volume ratio and the variations in the geometry and electronic structure have have a strong effect on catalytic properties. Suppose, for example, the reactivity of a small clusters the reactivity of a small clusters are found vary by order of magnitude when the cluster size is changed by only a few atoms. So the reactivity of a small clusters are found vary by order of magnitude. So when the cluster size is changed by a few atoms. So another application we can see in the hydrogen to metal. So all the metal do not absorb hydrogen. All the metal do not absorb hydrogen. Only few absorbs with a hydrogen to metal atom ratio of 1. So for small sizes, this property significantly enhances. So the number of absorbed atoms decreases with increasing cluster size. So this shows that small particles may be very useful in hydrogen storage devices in metals. So the application, here hydrogen to metal, all the metals do not absorb the hydrogen. So only few can absorb the hydrogen to metal of the ratio of 1. So for small sizes, this property is significantly enhanced when it is reduced. So this property is significantly enhanced, increases. So the number of absorbed atoms decreases with increasing cluster size. So that It shows small particles may be very useful in storage of hydrogen devices in metals. Hydrogen storage devices in metals. Optical properties. If the semiconductor particles are made very small, quantum effect come into play. So if we take a semiconductor particle, semiconductor in the sense of we can see semiconductor means that partially conducting material. Semiconductor is a partially conducting material. So in the semiconductors at 0 degree Kelvin, it doesn't allows or it does not conduct the current. When it increases or it attains room temperature, then it will conduct. So at 0 degree Kelvin, the semiconductor acts as a insulator, and at room temperature, it acts as a conductor. So that we called this as a semiconductors. Semiconductors. So if semiconductor particles are made very small, quantum effect comes into play, which limits the energies at which electrons and holes can exist in the particles. Okay, so when the semiconductor particle reduces to very small, so that it shows the quantum effect. So because of this, it limits the energies, so that is energy levels that electrons and holes can exist in the particles. So depending upon the nano size, that nano particle size, different colors can be seen. So gold nanospheres of 100 nanometer appear orange in color, while 50 nanometer nanospheres appear green in color. So this much of variation can be seen when bulk to nano-sized particles. So depending upon the particle size in the scale of nano, different colors can be seen. So this is one of the optical property of the nanomaterials. So it couldn't have seen in the bulk size. So here when taking gold nanospheres of 100 nanometers. So at 100 nanometers, gold can be appear as orange, orange. So when it is again reduced to 50 nanometer of sphere, what happening? So it appear as a green in color. Green in color. So as the energy is related to wavelength, as energy is related to wavelength, this means that the optical properties of the particle can be finely tuned depending upon its size. So, the optical properties of the particle can be finely tuned depending upon the size. Upon the size. So, which color we want, and so likewise we can reduce the particles size. Thus, particles can be made to emit or absorb specific wavelengths in the sense of colors. Okay, specific wavelengths of light merely by controlling the size. Particles can be made to emit or absorb specific wavelengths of lights merely by controlling their size. Coming to the electrical properties. In nanoscale, electrical properties depend on the size. For taking example, the resistance of a material, the resistance of a material is due to the scattering of conduction electrons with vibrating atoms and impurities. So the resistance of the material is due to the scattering of conduction electrons with vibrating atoms and impurities. So because of the vibrating atoms and impurities, so the electrons are scattered. The electrons, the conduction electrons will be scattered, so that when these electrons are scattered more and more, so there will be uh, more resistance. There will be resistance, so that the resistance occurs due to the scattering of conduction electrons with the vibrating atoms and impurities. So the mean distance traveled between two successive collisions. Two successive collisions. So suppose if we take a metal particle, metal element, so uh, there is freely moving electrons are there. Freely moving electrons are there. So when the electrons are scattered, so it will give rise to resistance. So as the electrons, conduction electrons scattered more and more, the resistance will be more. So the mean distance traveled between two successive collisions is called mean free path or scattering length. So if this electron is when it is approached to the ion, positive ion core, it may get affected, so that it may reflect. It may scatter. It may scattered, and it will collide with the other electrons. So that here what happens? The distance traveled between two successive collisions is called the mean free path. So the distance traveled between two successive collisions. So two successive collisions. Distance traveled between two successive collisions. This is the distance. Here the collision is. So the distance traveled between two successive collisions is called the mean free path or scattering length. So when the dimensions of the solid when the dimensions of the solid becomes comparable to this quantity, the scattering probability decreases, and hence electrical properties changes. When the dimensions of the solid becomes comparable to this quantity, the scattering probability decreases. So there will be electrical property change. Okay. So when the solid dimensions changes, scattering probability decreases. Scattering probability decreases, so that electrical properties got changed. When its size in the order of mean free path or de Broglie wavelength of electrons or holes which carry current, electronic structure of the system changes completely. Magnetic properties. So the strength of a magnet is measured in terms of coercivity, and saturation, magnetization values. So these values increases with the decrease in grain size. These values increases with the decrease in the grain size and an increase in the specific surface area of the grain size. So the strength of your magnet is measured in terms of coercivity, and the saturation, magnetization. values. These values increases, that is this coercivity and then saturation, magnetization are increases with the decrease in the grain size and an increase in the specific surface area of grains. So therefore nanomaterials present good properties in the field and so nanoparticles of even nanomagnetic solids are found to be magnetic. So it has been found theoretically as well as experimentally that the magnetism is special to small sizes and disappears in clusters containing more than 80 atoms. Containing more than atoms. So at small sizes, the clusters become spontaneously magnetic. So at small size, what happens? Clusters becomes spontaneously magnetic. Okay. So the magnetism is special to a small size and disappears in the clusters. Disappears in the clusters, which contains more than 80 atoms. Which contains more than 80 atoms. At smaller sizes, the clusters become spontaneously magnetic. So, clusters of nanomagnetic elements supported on magnetic substrate have also been proposed to be magnetic. To be magnetic. So, ferromagnetic and ferromagnetic multilayers have been found to exhibit giant magnetoresistance. Giant magnetic resistance, G and R. So, this is the table which gives the magnetism in bulk and in nanoparticles. So, we are taking a metal. So, how the change of the magnetism of that particular metal compared to bulk, how it will be in the clusters. How it will be in the clusters. So, if we take Na and K, that is potential, sodium and potassium. So, in bulk size, it will shows paramagnetic. It will shows paramagnetic. But when coming to clusters, it shows ferromagnetic. It shows ferromagnetic. So here in the second one, so ferrous, cobalt, and nickel. So it shows ferromagnetic in bulk size and in cluster super paramagnetic. Super paramagnetic. And here gadolinium and then terbium. It shows ferromagnetic in bulk size, and when in coming to the clusters, rotors are super paramagnetic. In chromium, it shows antiferromagnetic in bulk size. In clusters, frustrated paramagnetic. Here, rhodium, it shows that paramagnetism, while in the clusters, it shows ferromagnetism. So, this much of changes can be seen when it is reduced to nano size related to the magnetism. So, coming to the mechanical properties. So, most of the metals are made up of small crystalline grains, small crystalline grains. So, the boundaries between the grains slow down or arrest the propagation of defects. So, when the material is stressed, thus giving its strength. So, as we know that we take a crystalline solid. So, already we know that solids are crystalline solids and amorphous solids. Crystalline solids, regular and atoms are arranged in periodic and regular manner. And so, where in the amorphous, there will be disorder in the arrangement of atoms. Okay, so here most of the metals are made up of small crystalline grains. So this is of grains. This is the grain boundaries. So these are the grains, and this is the grain boundaries. Grain boundaries. So the boundaries between the grains slow down or arrest the propagation of defects. So when the material is stressed, thus giving its strength. If these grains are nanoscale in size, the interface area, that is this boundary interface area within the material greatly increases. These boundaries will be increases greatly if we reduce the size of the particle. So when the surface that is interface area, when the interface area greatly increases, it enhances its strength. It enhances its strength. So when we reduce the grain size to the nano, grain size to the nano, the interface area increases. This area will be the boundary area will be increases. The boundaries will be increases. So this will be increases. So because of this increase of interface area, increase of interface area, that is a increase of grain boundaries, it enhances its strength. It enhances its strength. So we have a grain. So when it is reduced, so what happens? Reduced, there will be increase of grain boundaries. So interface area will be increased so that it increases its strength. Strength. This is strength. Strength is increased. So for example, nanocrystalline nickel. Nanocrystalline nickel is as strong as hardened steel. If we take nanocrystalline nickel, is as strong as hardened steel because of the nano size. Many of their mechanical properties, such as hardness and elastic modulus, fracture toughness, scratch resistance, fatigue strength, and hardness, are modified. The mechanical behavior of nanostructured materials are greatly prepared by the method of gas condensation. Mechanical behavior of nanostructured materials are greatly prepared by the method of gas condensation. Superplasticity is the capability of some polycrystalline materials to exhibit very large texture deformations without nicking or fracture. So typically elongation of 100% to greater than 1000% are considered to the defining features of this phenomenon. So, as grain size is decreased, it is found that the temperature at which superplasticity occurs is lowered. So, grain size, if the grain size is decreased, if the grain size is decreased, what happens at a particular temperature? The superplasticity occurs lower, and the strain rate for its occurrence is increased. So that is, a superplasticity has been observed at somewhat lower temperatures. So superplasticity can be observed at lower temperatures and at a higher strain rates in nanocrystalline materials. So much differing results obtained so far suggest that very different mechanisms it may be causing superplastic behavior in nanocrystalline materials. So these are the properties of nanoparticles. So catalytic properties, electrical properties, magnetic properties, mechanical properties, optical, and biological. So coming to the catalytic properties, better catalytic efficiency through higher surface to volume ratio. Electrical property, increased electrical conductivity in ceramics and magnetic nanocomposites, increased electric resistance in metals. So, magnetic property, increased magnetic coercivity up to a critical grain size, super paramagnetic behavior can be seen. Mechanical property, because of this, improved hardness and toughness of metals and alloys, ductility and superplasticity of ceramics. Optical property, spectral shift of optical absorption and fluorescence properties. It increased quantum efficiency of semiconductor crystals. In biological, increased permeability through biological barriers. There is membranes, blood-brain barrier, etc. So it improves the biocompatibility. So these are the references. So engineering physics by K. Tyagarajan, McGraw Education, Private Limited, New Delhi. A textbook of engineering physics, M. N. Avathanulu, P.G. Sagar, S. Chand and Company, New Delhi. Engineering physics, Dr. M. Armugam, Anuradha Publications, Chennai, 6 class 17. Engineering physics, P.K. Palanisamy, 4th edition, Scientific Publications, Private Limited, Chennai. So these are the references, can give information related to this topic. Thank you.
Like, share, and subscribe. Hit the bell icon for more updates.